opportunity to present. I'm an associate of 2018 in the Earth and Planetary Sciences division of the Academy, and I'm presently working as associate professor at IIT Bombay. So as you announced, the topic of my talk is around the capturing and storage of carbon dioxide in India in our efforts to accelerate negative emissions, net zero targets by 2050 or 2060. So to begin with, I will do this animation here, which somehow is not playing. So here I'm just trying to reflect on the over the years how Asia, primarily China and India, have driven forward the consumption of coal. The scenario in Asia, primarily China and India, have been a lot of development that has happened in the last 2-3 decades, and it has been driven by the energy demands and the supply that has come from consumption of coal, and therefore, it is what is happening as a consequence, as we are aware that we are releasing large amount of greenhouse gases, primarily carbon dioxide in this case, that is leading to the increase in temperatures of the it may be useful to mention that there is a consensus that nearly 1 degree Celsius of temperature rise has happened in the last 1.5 century, or rather after the rapid industrialization began. And the question that is that around 40 years ago, when we talked about sustainable development, that there should be efforts of reducing the usage of fossil fuels globally. At that time, the contribution or the share of fossil fuel in the energy mix was up around 80%. And interestingly, 40 years down the line, when we are doing these discussions, even now, the share of fossil fuels is around 80%. So therefore, there are efforts that need to be expedited to essentially mitigate the effects of these greenhouse gases. So what I'm trying to show here, that through the records that we have, we understand that the temperature and the carbon dioxide emissions, they have some sort of an interrelationship, and subsequently it keeps on following it. And you can see that the two graphs, this is thousands of years before present, and therefore you can see that the graphs are more or less tallying. So one is the consequence and one is the effect. But also to be noticed here is that in the historic past, from now when the human civilizations, or we have the records, so the CO2 concentration was not above 280 ppm. In fact, till the 16th century, it is estimated that was the approximate concentration of CO2 into the atmosphere. But right now, we are aware that we have crossed around 420 parts per million. So there has been a rapid increase. So as this has been monitored, that's called as the Keeling curve, where we can see the temperatures have been continuously been rising as the CO2 concentration also has been rising, and the trend is to grow forward. So we all understand now that primarily the usage of fossil fuels, and among others, is responsible for this large amount of CO2. But where are the projections? They are saying here that presently we are at around 21, and then if we talk about 20 years down the line, we can clearly see that natural gas, coal, and oil, they are the fossil fuels that will be remaining. So although there are estimates for renewables to kind of sort of take over, but in the transition further, large amounts of carbon dioxide, the matter in question here. So we can see here in this case, this is from the limits database. We have tried to plot it around and look into the scenario till 2100, like end of this century. So we talk about reducing the CO2 emissions so that restrict the climate change to either 1.5 degree scenario or into a 2 degrees Celsius scenario. If no efforts are made, it will reach above the temperature change is expected to be around 6 degrees Celsius, and that will wreak a lot of havoc. So if we can see in the limits baseline, if we do not do, this is for India primarily, we'll be emitting up to around 16 gigatons of carbon dioxide annually. However, with all the pledges, we can limit it in years to come, around 2040, 50, we can get into the net zero emissions. And in case of the 450 scenario, will be going into that scenario. However, if we have just for the concurrent pledges that have been made right now, we'll be going into a scenario like this. However, the path can be defined if we are implementing all the scenarios that have been talked about. So what are the scenarios? It can be moving to the fuels, switching of fuels, going to nuclear, or it can be increasing the efficiency to 40%. And one of the other methods is the carbon capture and storage. So it's more or less imperative to consider carbon capture and storage in our ambitions for net zero emissions. It is expected that this is for 2 degrees Celsius scenario, 14%. But if we talk about 1.5 degree scenario and the capture that is required, it will account to around 32% of the all the efforts. So the door is closing, and we have the targets. And so what are the opportunities for doing that in case of in India? So as I mentioned about carbon capture and storage, so for this forum, where everybody has this understanding. So we can see that CO2 emission is happening right into the atmosphere. So there are large point sources of emissions from where it can be captured, where just like flue gas, where the concentration is around 14 to 20%. But in the direct air capture scenario, we are capturing directly from the 420 ppm. So there are various methods of doing the capture. But once it is captured, it is compressed and it is transported as a liquid or supercritical form, and then it is taken into the subsurface reservoirs, where there are ample amount of pore spaces where it is going to be pumped inside, and it is expected to remain there for geologically significant periods of time. That's where the interest that comes, that for me, and India is so geologically diverse, we need to look into these availability of these pore spaces where the injection can be carried out. So often the question is the volumes of CO2s. Yes, there are like gigatons of CO2 already being emitted, and also we talk about the huge volume here. So we see that when we go into the subsurface, we typically have our targets of injection at around 800 meters or deeper. So at that pressure temperature, we cross the critical PT conditions for carbon dioxide. That's 31.1 degrees Celsius and 7.38 megapascals. And at those depths, it becomes supercritical. It has different properties, and it can get stored in a very like a tiny droplet for each big volumes of CO2. So the natural analog for this is the oil and gas that was formed several thousands of years, and in case of coal, millions of years ago, and that has remained in place into the subsurface reservoirs. So taking forward, there are different scenarios, situations in which carbon dioxide can be stored in the subsurface. One of the most common that has been in practice in globally is the oil and gas recovery, enhancement of oil and gas recovery. However, in India, we do not have any project where CO2 is injected for enhanced oil and gas recovery. So here the CO2 is injected, and it mixes with the oil that is there. It drives the oil. There's a miscible zone, if you can notice here, and from the miscible zone, oil is pushed towards, and it is come out. So the oil comes out. So the CO2 is separated from the oil, and it is again reutilized. So in that process, also some amount of carbon dioxide gets stored. Around 30% of CO2 gets stored in the reservoir. Once this reservoir is drained completely to the target that we have, and it is not considered further, this becomes a really interesting reservoir for storage of carbon dioxide, additional amount of carbon dioxide, because we know about the reservoir far better. We know about the stresses, presence of the distribution of stresses. We know about the pore pressure. We know about the overall strength and integrity of the system. So that is often considered as a good reservoir for storing carbon dioxide. Then we have the deep saline aquifers. That's in the India has a big peninsula, and we have the offshore, that is deep saline aquifers, that are present to significant depths, and there also we have the potential for storage of carbon dioxide. Then we have a large amount of deposits of basalts in the country, whether it is the Deccan traps or the Rajmahal traps, where primarily CO2 can be injected, and it can transform into through mineral carbonation into stable carbonate minerals, and therefore it can be sealed inside the subsurface permanently. And then there is another scenario where coal bed methane is, as a natural gas, is being tapped. Earlier, when brine was produced, oil was like a problem, and then later we realized that it's actually the oil we should be mining out. Similarly, while coal mining, CBM was a big problem, and it is typically burned out. But now coal bed methane and coal mine methane are considered very seriously. They are tapped as energy sources, and therefore that becomes relevant. Another storage space can be the methane hydrates. Again, in the offshore of India, primarily the offshore, there are huge deposits of hydrates, and several hundreds of trillions of cubic feet of natural gas has been identified in those hydrate deposits. So theoretically, the substitution of methane by CO2 can also lead to carbon dioxide storage. So these are the general scenarios where the injection can happen. Now, the big problem is to understand the potential that India has for geologic carbon storage. So often, if you look at the global map of CCS, whether you're talking about most of the countries like China, Australia, USA, Canada, or the European Union, most of these places there have been studies done to understand the CO2 storage in terms of their oil and gas fields, deep saline aquifers, or any other top type of reservoir. However, it may be noticed that India here is like a blank spot. So there is a requirement for doing those studies. In fact, I was referring to the Energy Outlook of 2021 that is released by International Energy Agency in Paris. Among other grand challenges of the century, they have identified, let's say, lithium-ion batteries or hydrogen. CCS also remains important here, and India's CO2 storage potential has not yet been properly mapped. So last year during the lockdown, it was a very good period for us to sit down in our houses. I mean, relatively no access to the lab, so we used that time very productively, and I can show that we have now tried to build the geological storage potential map for India. So although I have like separate maps for each of these scenarios, I've tried to bring them all together, that my group here has worked towards this work. And we can see that we have tried to figure out the storage capacity in the saline aquifers, where they are whether they are the offshore or the onshore saline aquifers, or we have tried to map the potential for enhancement of oil recovery, whether it is the Mumbai offshore or the Cambay Basin here or the northeastern part of the country. And then also looking into the basaltic formations, whether it is the Rajmahal traps out here, or it is, sorry, the Rajmahal traps on this side and the Deccan traps on this side. So collectively, we have attempted to come up with this storage map of the country, where we can now look into the capacities of each types of reservoirs and their distribution, and the amount of CO2 that can be injected here. So as I was talking about the scale, here you can see that we have the potential to store in orders of tens or hundreds of gigatons of CO2 in the country. I think this is enormous amount of potential that India has. However, we must understand that what we are working out right now is primarily the theoretical, effective, or viable capacity. But a matched capacity, which is like on the top of the pyramid, is a more certain capacity. However, that capacity can only be confirmed when we actually do the injection. So we have tried to map for the enhanced oil recovery scenarios, and we can see that there are in orders of gigatons we can inject and store the carbon dioxide. So this is one of the work that we did last year. It is currently under review. Now we have talked about the national scale. However, we need to understand that each reservoir will behave very differently, even from basin to basin, within the basin, from one layer to the other layer, the properties of the rocks vary significantly. So all of them need to be studied in good details. So what we do in our lab here, we collect field samples, sometimes from the outcrops, sometimes from the open cast mines, and quite often we now have access to the samples from the subsurface drilling. And we collect the samples, we kind of simulate the subsurface condition in the lab here, and in that we tend to pass the different phases of gas, let's say CO2, methane, nitrogen, and we try to see how the flow and deformation of these substrata is happening, or the rock sample is happening because of the flow of this fluid. And that will actually lead us to the understanding of the reservoir. So as I said, each reservoir is different. These samples need to be tested in a proper way, and these become actually input into our the whole of modeling that we do for the basin scale. So from the field scale, we have come down to the core scale to integrate towards the basin, and we do these experiments of porosity, permeability, strength, and other aspects to kind of understand the fundamental behavior of these systems. So what is important here to understand that a sample that is saturated with carbon dioxide will not behave the way it is when it is unsaturated, or it's like the natural sample that we get from the field. Its properties will vary significantly. Just for example, I've tried to show here in this graph that the strength of a coal sample that is treated with carbon dioxide, then it will be different from that of otherwise. So here the strength is coming around 12 megapascals, while the untreated sample had a strength of around 18 megapascals. Now, through the acoustic emission studies, also we have tried to identify the failure patterns. So we can see that the failure pattern is sort of varying and it does not really fail like an integrated system. There has been a deformation that is already happening. So parallel to this, we also try to use these data as inputs to our reservoir scale model. So a simplistic scenario where we have put a CO2 injection well in the center, and we have methane coming out from this here in an enhanced CBM scenario. We inject the carbon dioxide and methane is coming out. So CO2 essentially drives the methane production process. However, the interesting part findings of our study says that approximately 3 to 4 times volume of CO2 can be stored for each volume of methane that is recovered. So there is preferential absorption, and this is done for Raniganj and Jharia Basin. We can see that the methane production that would have gone in a trajectory like this, actually, because of CO2 injection, it kicks off further. So our enhancement of methane recovery is also happening. So it's like a beneficial scenario where we are actually using CO2, pumping it for permanent storage, and actually enhancing the methane recovery. So that's collectively addresses the problem of somewhere climate change mitigation, but also enhanced energy security, as the government of India envisages that we need to gas-based energy from 7% right now to 15% in a couple of years from now. So these sort of exploration and production will lead to a better strengthened scenario. So we also get into the more detailed fundamental into these rocks. So I talked about the core scale, but now I'll just briefly mention that we go into the pore scale about these systems. So we try to identify. So this is an example from a CT computer tomography out here. So we scan the rock block, and within the rock block, each of these slices are integrated together to figure out where exactly the pores are and the pore networks are. So if we process, and the rock block would look something like this, we can separate the matrix block like in a different way, and we can move out the pore network in an architecture in a different way. And when we have separated the pores, we can actually separate the green colored, the connected pores, and the non-connected pores. So these level of understanding is allowing us now, globally, to understand. And when we talk about the percentage recovery, we often do not know about the denominator. We are talking mainly about what the gas is being produced or oil is being produced. But because now with this understanding, we have now identified that these methods can be used to collectively understand the reservoirs better. So that is another effort that we. This is a scenario where and just take it as an example for. A site identification. Often there is confusions about induced seismicity and problems related. So this comes from saltwater disposal, and you can see that here in the scenario, the water is being disposed in a very safe and secure reservoir. However, in this case, when the water goes here, you can see that the water essentially flows into a fractures, and it can actually turn on the fractures and lead to some sort of seismicity. So that sort of understanding is the reservoir is required. What we essentially work here is the gap between the pore pressure and the least principal stress, and that becomes interesting because when we do carbon dioxide injection, we're actually increasing the pore pressure. So the next point that often we have to understand whether India is ready to implement CCS or not. So I thought I'll just compare the global technological readiness level, talking from TRL1, that is conceptual, to a commercial scale. Several of the technologies in the global level in terms of capture, transport, storage, and utilization, they are in pretty much an advanced stage where pilot and demonstration or commercial scale projects are going on. However, when we tried to do this map for India, where we are talking about the capture, transport, and storage or utilization, and we compare it from the global state of the art or whether we are advanced, we can see that in India, most of these studies are at proof of concept and lab prototype scale. So I think there is a requirement now to expedite our studies to where we can advance the TRL from 2, 3, 4 to somewhere around 8, 7, 8, or 9. And this is likely to happen because the industries are taking a lot of interest in the aspects of carbon capture, utilization, storage, looking at carbon dioxide as a commodity rather than as a burden. So before I end, I would also want to talk about the storage readiness level, because just like TRLs, where we have talked about technology, we also need to understand how ready our reservoir is for the storage of carbon dioxide. So this is an example from another paper that was published, or rather pre-printed this year. And from there, we are trying to work around storage readiness for India. So therefore, we need to have this effective matching of the source and sink, and then understand that India is going to be, contribute significantly to the global CCS chain by 2060. That's around 20% of it. So India holds the future for it, and the R&D that we are doing shall be very useful. This slide I often put here. The model developed in our group here, one of the students did it. And it's so interesting that when we look at it, it looks like a nice numerical simulation where we can see that some plume of gas is rising in a reservoir. However, interestingly, it's not really a numerical model. It's rather a physical model and you can see that the CO2 is being injected here at the base, and it is rising by the contrast in density or the buoyancy here, and the CO2 is being stored out here, and it's like the different trapping mechanism, whether stratigraphic or structural, and there's some amount of dissolution and mineral trapping that is out here. So, and then we have developed this model also primarily to communicate the principles of CCS to non-specialists. So I would like to conclude here that there is ample amount of scope to work on CCS in India, and primarily, we have to advance the TRL and SRLs. So these are some of the contributions that we have done here, and primarily the CCS roadmap that the government of India, published, and I happen to co-author there. It is giving the guidelines that we can consider CO2 eCBMR and CO2 EOR as one of the steps. So I'd like to acknowledge the opportunity here, and thank you very much for your attention.
Thank you, Vikram, for a very, very fascinating talk. There are a couple of questions for you. The first one is from Rakesh Mishra, who really wants to ask you how, I think his question is related. You've told us about the carbon storage, but I think he wants to know, okay, once you store it, can you recover it? Or how would is recovery possible, or is the principle of storage doesn't have anything to do with recovery?
So if I have to just talk about the EOR process, enhanced oil recovery, there when the carbon dioxide is injected, when there's miscibility that is happening, oil mixes with the carbon dioxide and it pumps itself outside along with the oil. So that CO2 is recovered and it is separated and reused. When we talk about coal bed methane, we actually inject it and CO2 just pushes out the methane. It is preferentially taken up and gets stored. When we talk about the deep saline aquifers, it is essentially pumped inside and it stays there because of the compression of the forces that are present there, just like the oil in a conventional reservoir system. So if we want to, and for some reason, if we have to produce, we can actually depressurize the reservoir and produce the carbon dioxide. However, the aim here is to have a permanent storage of carbon dioxide in the subsurface.
Excellent. Okay, the other question is from Deepak Srivastava, and he wants to know what is the porosity of basalt, because basalt is quite dense. So how much,
yes,
can you really, compared to, let's say, I don't know, laterite or Aravallis and, limestone and things like that?
Yeah. Thank you, ma'am, for a very interesting question. So basalts almost have negligible porosity. There's some porosity because of the gases that get released when the magma is cooling. So we have, these are very tight systems compared to any conventional reservoir, which can have several percentage of porosity, 10, 20 to 30% also in some cases. In cases of shale, it's highly porous. However, in basalts, the idea here is that when we inject in basalt, it has to be stimulated. The system has to be stimulated by creating some sort of fractures. Identify also within the basalts when there are some angles or some buckling that happens, that also leads to some amount of fracturing at the contact between the intertrappeans. So these are the sites that we typically would have to identify. And when we pump it, it has to be stimulated so that the CO2 can migrate through this reservoir, and it gets maximum exposure to the surface area of basalt, so that there can be interaction between the gas and the minerals in the basalts, so that it transforms into a carbonation process. So interestingly, in terms of storage mechanisms, this is considered as the most difficult, and also considered as it will take mineralization is supposed to happen in hundreds of years of time scale. However, the experiment that was done in Iceland and published in Science in 2015, they actually did a pilot scale of study of injection where they stimulated the basaltic strata and injected CO2. And interestingly, around 95% of carbon dioxide that was injected transformed into a mineral phase in less than 2 years of time. So this is a renewed interest that has come into basalts. However, if we talk about compared to the conventional reservoirs, it is a far more challenging scenario because it does lack porosity and permeability.
Excellent. Very nice. Very interesting. So I have a question for you.
Yes,
where you talked about seismicity and fault lines. And I think we also have issues about fracking. Yes. So how does, if I understand it also, fracking is also, often frowned upon because of the possible rise in, fractures. So what is your take on fracking? And so that's my first question. And then I have another question for you, and then we'll wrap up.
Sure,
So
ma'am.
what's it? Yeah.
Yeah, in fact, there's a very interesting study that was published in Science Advances in 2017. There, they have actually figured out, primarily looking at fracking scenario in Oklahoma. That's the one of the places where lands have been evacuated because of loss of size. So essentially,
Yeah.
it was found that rather than the fracturing process, when we are taking the waste water that comes out that is used for fracking, when we are disposing this wastewater, when they are injected into sites which have a lot of pre-existing fractures at a critical stress conditions, when they get triggered, these are the ones which actually cause seismicity rather than the process of fracturing itself.
I see. Okay, excellent. And now my last question to you is, what is the interaction between gaseous or carbon, however it is being introduced into the pores, and interaction with existing water? Because a lot of,
Sorry.
interaction, when you're talking about introducing carbon into, porous media, like let's say basalt, and we talked about that. What's the relationship between carbon and water?
Yeah. So,
You could
carbon
have
dioxide.
Yeah.
Sorry. If I got the question right, ma'am, two things again in the picture here. So if the CO2 is interacting with water, it will form a weak carbonic acid that may have a reaction to the minerals that may be present. However, again, because we are doing this injection at a certain depth below which we don't really reach to as aquifers that is used for any sort of water that is used for any purpose. Let's say our aquifers are not as deep as 800 meters, where we are actually targeting to tap water for any sort of usage. So there may be interactions, but it is not likely to affect our environmental concerns around water storage.
Okay, okay. Thank you very much, Vikram, for a very interesting talk.
Thank you for the opportunity, ma'am. Thanks.
Yeah.